بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is the first lecture in the course Math 101 Finite Mathematics, and the book used for this course is called Mathematical Applications for the Management, Life and Social Sciences, the 12th edition. We will start by the first section of chapter 0 of this book, which is about algebraic concepts. So chapter 0 is about some algebraic concepts, and the first section is about sets. A set is a well-defined collection of objects. So any collection of objects will be a set. We may talk about a set of books, set of dishes, set of students, set of individuals with a certain blood type. And there are two ways to tell what a given set contains: the elements inside the set. How? The first method is by listing the elements or the members of the set. And the second method is to say the elements inside it, say a characteristic that satisfied by all the elements inside it. So, for example, we say that a set A contains 1, 2, 3, 4 by just writing set A equals 1, 2, 3, 4. 4 is an element of the set A. We just use this notation. We say 4 belongs to A, or 4 is an element of the set A. If we write like this, this means that 5 is not an element of A, of the set A. If all the elements of the set A can be listed, the set will be called finite set. So for example here, this set has 4 elements, and this set B has 3 elements. So these are finite sets. We can, if the elements inside the finite set are very large, for example, set of even integers from 8 to 8,952, we can write 8, 10, 12, 14, 3 dots, and the last element. So this means there are a lot of elements between 14 and 8,952. We don't have to list all of them if it is known, okay? If the elements are known. If we cannot, of course, for the infinite set, we cannot list all the elements. So what should we do? We use the 3 dots at the end. So for example, this set, capital N, set of all natural numbers. This is a very famous set. So what are the natural numbers? 1, 2, 3, 4, and so on. So these 3 dots means 5, 6, 7 until infinity. So this is an infinite set. It's not finite like this one. The second way to specify the elements of a given set is by description. So instead of listing, you can describe. So for example, if you write set D consists of all X such that X is a Ford automobile, you are describing the set of all Ford automobiles. Okay, and this is how do we read it? X such that X is a Ford automobile. Another example, capital F is the set of all Y such that Y is an odd natural number. So you can write it like this by description, and here also you can list the elements, because the odd natural numbers are 1, 3, 5, and so on. Okay, so this is an infinite set. So either you describe the set or you list the elements inside the set. Let us see this example. Write the following sets in 2 ways. The set A of natural numbers less than 6. natural numbers less than 6. So 1, 2, 3, 4, and 5. So this is the set A by listing the elements. In two ways we can describe, we can say that A consists of all elements X such that X is a natural number, natural number less than 6. So this is another way to write this set by describing. The set B of natural numbers greater than 10. So we can say, we can list the elements inside B, natural numbers greater than 10, so starts by 11, 11, 12, 13, and so on. Or by describing, you can say B consists of all elements X such that X is a natural number. So you can say X belongs to N natural numbers and X is greater than 10. Okay, this is another way of describing, or you can just say X is a natural number greater than 10. Or you write it like this: X belongs to natural numbers and it's greater than 10. So it has 11, 12, 13 up to infinity. This is an infinite set. The set C containing only 3. So there is only one element inside C. Or by describing, I can say this consists of all X such that X is 3. So C consists of one element, which is 3. A set that contains no elements is called the empty set or the null set. Okay, so the empty set has no elements, and we denote it by this symbol, which we read phi. Okay, this is called phi, Greek letter, or by just writing like this: two braces without two parentheses without anything inside them. The set of living veterans of the War of 1812 is empty because there are no living veterans of that war. So we can just say that this set, which consists of all X such that X is a living veteran of the War of 1812, is phi. It's an empty set because they are all dead. Now, some relations between sets. We say that two sets are equal, X and Y, if they contain the same elements. So for example, this is X, this is Y, they have the same elements. The order is not important. Inside the set, you can say 1, 2, 3, 4 or 1, 3, 4, 2, as you wish. The order inside the set is not important. We understand from here that Y has 4 elements. What are the 4 elements? 1, 2, 3, 4. So X is equal to Y. A is a subset of B, okay, which we write it like this: A is a subset of B if every element of A is an element of B. So all the elements of A are elements of B. Then we say that A is subset of B. The empty set is a subset of every set. Okay, so phi is a subset of every set because phi has no elements. So it's a subset of every set. Each set A is a subset of itself. So we can write that A is a subset of A and B is a subset of B because all the elements in B are in B. So for example, this is the set A, 1, 2, C, F, and this is the set B. Notice 1 is in A and it's in B, 2 is in A, it's in B, C and F are also in A and in B, so A is a subset of B. A is a subset of B. Also, phi is a subset of A, subset of B, and A is subset of A, B subset of B. So for any set, there are two known subsets always, phi and the set itself. If C and D have no elements in common, we call them disjoint. So there are two sets with no elements in common. So we say that the two sets are disjoint. For example, set C 1 2 AB, set D 3 E 5 C. The members here, the elements here are different than the elements here. So these two sets are disjoint. We always, when we talk about sets, there is an assumption that's always made that these sets under discussion are all subsets of some larger set, which we call the universal set U, capital U. We denote it by capital U. So any sets we talk about are always subsets of a larger set, which is the universal set. We may use also Venn diagram. What is the Venn diagram? It is a large rectangle, represents uh, the universal set U, okay, like this one, the universal set U, and inside U, you have the sets. Okay, so a rectangle represents the universal set, and closed figures inside the rectangle represent the sets under consideration. For example, here, this is the universal set, and here we have a set A and a set B. So we can see that B is a subset of A because B is inside A. So any element of B is an element of A. So B is a subset of A. Here we can see that M and N are disjoint because no elements in common. Okay, all the elements of M are different than the elements of N, so M and N are disjoint. X and Y here are not disjoint because these here we have elements in common. Here we have elements in X and in Y at the same time. So X and Y here are not disjoint. Let A be this set, B this set, and C is this set. So we have three sets here in this example. Use these sets to answer the following. Of which sets is 6 an element? So 6 is not in A, 6 is in B, and it is in C. So B and C. So 6 is an element of B and C. Of which sets is 2 a subset? Okay, so this would be a subset of all the sets that has this element, which is 2. So we have 2 here and 2 here, but there is no 2 here. So this set is a subset of A, and also it's a subset of B, capital B. Which of the following are true? 2 is an element of A. Yeah, correct. This set is an element of B. Well, this is false, okay? Because it would be an element if inside B we have the set, okay? In this case, we say that this set is an element in B. But in fact, this is not correct. What is correct here, what you can write here, we can write that this set is subset of B, but we cannot write belongs to because it's not an element. 2 is an element of C, no, so this is not correct. 5 is not in A, no, 5 is in A, so this is false. 5 is not in B, yeah, 5 is not in B, is not an element of B, so this is true. Which pair of A, B, and C are disjoint? A, B, is it disjoint? Are these two sets disjoint? No, because 2 is in common. There is 2 here and 2 here. What about A and C? 2, 3, 5, 7, 11, 6, 10, 14. Yeah, A and C are disjoint. There are no elements in common. So A and C. These two sets are disjoint. Okay, what about B and C? 6, 6. There is 6 and 10 also, so they are not disjoint. So the only two disjoint sets are A and C. Which of phi A, B, and C are subsets of the set P of all prime numbers? Well, the prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, and so on. All of these numbers cannot be divided by any other numbers except by 1 and the number itself. Okay, these are called prime numbers. So phi is phi a subset of B? Of course, phi is a subset of any set. So phi is okay. We can say, we can just write the sets. So phi, okay. What about A? Let us look to A. 2, 3, 5, 7, 11. Yes. 2, 3, 5, 7, 11 are all prime numbers. So A is a subset of P. What about B? Let us look to B. No, there is 4. 4 is not a prime number. 6 is not a prime number. So B is not a subset of P. What about C? 6 is not a prime number because you can divide 6 by 3 and by 2. 10 also is not a prime number. So the only subsets of P are phi and A. Phi and A. Okay. The set M of all multiples of 2. Multiples of 2, the multiples of 2 are 2 and you multiply by 2. So 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10, 12, 14, 16, 18. So you just multiply 2 by a number, by 1, by 2, by 3, by 4, by 5. All of these are called multiples of 2. So is A a subset? No, 3 is not a multiple of 2. While here, all of these numbers are multiples of 2, and all of these numbers are multiples of 2. So we have phi subset, B and C are all subsets of capital M. Which of A, B, and C is equal to D, this set? Let us try to understand this set first. So D consists of all x such that x equals 4n plus 2 for natural numbers from 1 to 5. So let us replace n by 1. 4 times 1 plus 2, 6. 4 times 2 plus 2, 10. 4 times 3 plus 2, 14. 4 times 4 plus 2, 18. 4 times 5 plus 2, 22. And we stop at 5 because small n is between 1 and 5. Now, what is this set? Is it A, B, or C? 6, 10, 14, 18, 22. This is the set C. So D is equal to C. They are equal because they have the same elements. Set operations. The set containing the members that are common to the two sets is said to be the intersection of the two sets. Okay. So what is the intersection? It is the set that has the members that are common to the two sets. So A intersection B, we read it A intersection B consists of all x such that x is in A and also x is in B at the same time. So x is in A and in B at the same time. If x belongs to A and B at the same time, it would be in the intersection. So that's the intersection. So for example, we have AB, find A intersection B. So A intersection B would consist of all elements. 2. Is 2 here? No, 2 is not in B, so 2 is not in the intersection. 3 is here and here, so 3 is in the intersection. 4 is here, but it is not here, so it's not in the intersection. 5 is here and here, So 5 is in the intersection, and the intersection has only 3 and 5. Which of A, B, and A intersection B is a subset of A? All right. A. Is it a subset of A? Yeah, we say any set is a subset of itself. Okay, what about B? Is B a subset of A? No, because B has 7, for example, and 7 is not in A. So B is not a subset of B of A. What about A intersection B? Is it a subset of A? Yeah, the elements in A intersection B are 3 and 5, and 3 and 5 are here in A. So A intersection B is a subset of A. So always the intersection, in fact, is a subset of A, and it's also subset of B, the intersection. The second operation, the union of two sets. And it contains all members of the two sets, all members together of the two sets. So the union of AB is written like this: A union B. It contains all X such that X is in A or X in B or both. So X would be in the union if it is in A alone, or in B alone, or in both of them. It would be in the union. So the union has everything. So for example, this is capital X and this is capital Y. Find X union Y. Well, X union Y would be, I write the elements of X first, A, B, C, and F, and then I add the elements of Y. E is not here, so I write it. F is already here, so there is no need to write it again. Also A, B is also here, so I don't write A, B, and F. So this would be the union of the two sets. Intersection of A and B, this is the intersection, the elements of A and B at the same time. And the union of AB has everything. So this is the Venn diagram of the intersection and the union. Example, A consists of all X such that X is a natural number less than 6. So what is a natural number less than 6? Natural numbers are 1, 2, 3, 4. So less than 6. So you will have up to 5. So this is in fact capital A, and this is the set B. And we need to find the intersection. Well, A intersection B would be 1 is here and here, so 1 is in the intersection. 3 is here and here, so it is in the intersection. 5 is here and here, so it is in the intersection. 7, 9, 11 are not here, so this is the intersection between A and B. The union, A union B. To find the union, everything. So I will write set A first, which is 1, 2, 3, 4, 5, all elements in A. And then I add the elements of B that are not in A. So 1 is the 3 is there, 5 is there. So I add 7, 9, and 11. So this would be A union B. Another operation, all elements of the universal set U that are not in A are called the complement of A. So what is the set complement? We denote it by A complement like this, A prime, A complement, and it's defined by all elements X in U such that they are not in A. So they are in U but not in A. So using Venn diagram, if this is A, then this is a complement. All the elements outside A are in A complement. So you can notice that A union A complement would give you U, the universal set, and A intersection A complement is in fact phi. There is no intersection between A and A complement. So you can say that A and A complement are disjoint. Example 5, if U is a set of natural numbers less than 10, so this is the universal set. So what is the universal set? It is natural numbers less than 10. So we start from 1, 2 up to 10. A136, B1689, find the following. A complement. Well, A complement would be the elements in U that are not in A. So 1 is in A, so it's not in A complement. 2 is not in A, so it is in A complement. 3 in A, so it's not in A complement. 4, 5 are not in A, so they are in A complement. 6 in A, so it's not in A complement. 7, 8, 9, 10 are in A complement because they are not in A. B complement. Well, we have 1, 6, 8, 9. So the elements in U that are not 1, 6, 8, 9 are in B complement. So 2, 3, 4, 5, 7, and 10. We have 10 elements in U, 4 of them in B, and 6 in B complement. How to find A intersection B complement? You can find A intersection B first, and then you can find their complement. So what is A intersection B? This is A, this is B. 1 and 6 are here and here. So 1 and 6 are in the intersection. So what is A intersection B complement? All elements in U that are not in A intersection B. So all elements in U except 1 and 6. So we have 2, 3, 4, 5, 7, 8, 9, and 10. A complement union B complement. Well, this is A complement, okay, and this is B complement. Let us find their union. So I will write A complement as it is 2, 4, 5, 7, 8, 9, and 10. And let me search now in B complement. Is there a number which is not here? 3. Okay, so I add 3. 4, 5, 7 are here. 10 is here. So only I add 3. Now please compare these two sets, C and D. You will find that 2, 3, 4, 5, 7, 8, 9, 10 exactly the same. So in fact, there is a characteristic that says if you want to find the complement of A intersection B, you find the complement of A union the complement of B, and this is a very famous formula. Checkpoint. Given this set, these sets, this is the universal set. This is A, B, and C. Find the following: A union B. I leave this for you. Okay, B intersection C. You should be able to find it by now. And A complements. Example 6. Suppose an investment advisor monitored several stocks for clients and on a certain day categorized 23 stocks. So we have 23 stocks in total. Their closing price on the previous day was less than $50. Let us call this C. Their price to earnings ratio was less than 20. Let us call this capital P. Their dividend per share was at least 1.5. So let us say that this set is D. So we have three sets, C, P, and D. If we draw the universal set, so this is the universal set U, okay, and we have set C, set P, and set D. So these are the three sets, C, P, and D. Of these 23 stocks, the total number of stocks is 23. 16 belong to set P. So P has 16 elements, but some of them are here, some of them are here, some of them may be here, some of them may be here. So let us wait a little. 12 belong to set C, similarly. 8 belong to D. 3 belong to both C and D. Both C and D, both C and D here in this area. In this area, we have 3, but maybe some of them here, some of them here. So what is this area in the middle? This is the intersection between C, P, and D, all the 3. So when he says here, 2 belong to all 3 sets, so in fact, I have 2 elements here. Okay. Now, if you go back here, 3 belong to both C and D. Both C and D, which is this area, there are 3. Okay, 2 of them here, so I'll have 1 here. So I have 2 plus 1, 3 between C and D. In C and P, in the intersection of C and P, I have 10. Okay, 2 of them here, because this is the intersection between C and P. 2 here, so I will have 8 here. So the total is 10. 8 plus 2 is 10. 7 belong to both D and P. So here in this intersection between D and P. Well, 7, I have 2 here, so 5 would be here. 5 plus 2 is 7. So now I finished from the intersection of all the 3 and the intersections of each 2. And now I go to these 3 information. 16 belong to P. In P, I have 16. Up to now, I have 8 plus 2 plus 5 in P. So 15 in P, but there is 16, so still one of them here. Okay. In C, I have 12. 8, 2, 1, 11. I have 12, so still one of them here. 8 belong to set D. 5 plus 2 plus 1 is in fact 8. So there is nothing here. There is 0 here. Okay, how many elements in total? If you add all of these numbers, I have 1 plus 8 plus 1, 10, plus 1, 11, plus 2, 13, plus 5, 18. But the total number is 23. So if you subtract 23 minus 8, is it 18? Let me check again. 10, 15, 18. Yeah, minus 18, it is 5. So I have 5 stocks outside these 3. So this is a Venn diagram that enables you to illustrate the problem, and using this Venn diagram, you can answer all the questions. So for example, part A, how many stocks had closing prices of less than $50? That's what? That's C. Okay. So he's asking about C, per share, or, so or means union, price to earning ratio of less than 20. Less than 20, that's P. So he's asking about C union P. Okay. How many stocks? So you just add the elements, the stocks inside C and P. So I have 1, 8, 1, 10 plus 5, 15 plus 3, 18. All of these numbers are in C and B. So I have 18. Okay. How many stocks had none of the characteristics of C, P, and or D? So it's not here, not in any one of these. So we have 5 outside. So the number is 5 stocks. Okay. How many stocks had only dividends per share of at least 1.5? So only D. Okay. So only D. Only D means uh, it is only D. It is not in P and not in C. Well, there is nothing in only D, 0. If it is only P, there will be 1. If it is only C, there will be 1. But only D, there is nothing, 0. So none of the stocks has only dividend per share of at least $1.5 because no stock is here. This is an exercise from the book, and this is the last point in the class, the difference of two sets A minus B. So this is the definition of the difference of two sets. It is defined as the set containing all elements of A except those in B. So all elements in A but not in B. So you remove the elements of B from A. Also, you can check that A minus B is A intersection B complement. So if you want to find A minus B, you can find it in 2 ways. For example, here in this question 43, A minus B would be, okay, 3, 1 is in A, but it is not in B, so it is in A minus B. 3 is in A, but it is in B, so you remove it. 7 is in A and it is not in B, so it will be in A minus B. 9 is in A, but it is in B, so we remove it. So A minus B consists of only 1 and 7. If you want to solve it like this, let us find B complement, okay? So this is B. What is B complement? This is U, the universal set. So B complement would be 1, all the elements not in B. So 1, 2, 4, 6, 7. Okay, how many elements here? 9. Here 4. Here should be 5. Yes. So how to find now A intersection B complements? A intersection B complements. So this is A. Find the intersection between A and the B complements. Okay, 1 is here and here, so it is in the intersection. 3 is here but not here. 7 is here but and here, so 7 is also in the intersection. 9 is here but it is not here, so it's not in the intersection. So this is A intersection B complements, which is also A minus B. So you can find A minus B in two ways. Let me find A minus B here for this question. Again, 1 is here, so you remove it. 2 is here but not here, you write it. 3 is here and not here, you take it. 6 is here but here, you remove it. 9 is here but not here, you take it. So A minus B, if you remove these elements from here, you will find 2, 3, and 9. So this is A minus B. Here, if you remove these elements, 1, 2, 3, from here, 1, 2, 3, 5, if you remove it from here, you will find that A minus B is in fact phi, okay? Because all the elements of A are in B. While here, the 7, 8, 9 are not in A. So you can say that these two sets are disjoint, in fact. So A minus B in this case would be just A, all the elements of A. Thank you very much. This is the end of the first section, section 01.